Hey everyone, lesson 26 coming at you here from the grade 11 online physics class. Relative motion and scalars and vectors is the next up. So let's get into it. Let's play a little game called Am I Moving? And so I'll finish that in a bit. If you're sitting in a chair, most people are going to answer no, right? Or if you're walking, most people are going to answer yes, right? The trick is, can you describe a situation in which the opposite would be true? So if you're sitting in a chair, is there a situation where you'd be sitting in a chair, but you are moving, right? So this is if the chair is on the floor in a room, you're automatically probably visualizing you're sitting in a chair right now. Is there a chair you could sit in where you'd be moving? Well, what if the chair was on a boat or a bus or a car or whatever? So you're sitting down in a car or a bus or whatever. The bus is moving, so you're moving, right? Or what about if you're walking? Any school bus riders amongst us? So if you're walking backwards and the bus starts going forwards and you're walking at the same speed as the bus, you'd basically be staying still for a little bit. You might have experienced that kind of thing, right? You'd be like these friends outside the bus and you're walking and you're staying in line with them as the bus pulls ahead. Bus drivers probably aren't supposed to do that, but in the name of physics, we should allow it. So the answer is could be no. You could be on a treadmill. I wasn't talking about that one yet. Or you could be walking backwards in a bus, right? So you could be walking along on a treadmill. It's an easier example, I suppose. But the neater one is that's a word, I guess. The more interesting one is walking backwards on something that's moving forward and canceling out your speeds. And you just kind of notice these kind of things, right? You might have noticed it yourself in just in life experiences so far. So the better question with extra information included would be, are you moving? And the question is, are you moving relative to something? Okay, and that's what we mean by reference or relative motion. Are you moving relative to something? And the thing that you're moving relative to, we call a reference frame. Okay, so to fully describe motion, you need a reference frame. So you describe your motion relative to it. So the most intuitive frame of reference for us as human beings living on planet Earth is planet Earth itself, right? So are you at rest or moving relative to planet Earth? That's the most fundamental one we tend to think of. This little video here, hopefully I don't get dinged with copyrights. I say that a lot. Let's see it. I have it running at 1.5. So let's see if we can.
Professor Dave here. Let's talk about relative motion.
So it sounds a little fast right now. Actually, too.
That physics is concerned with the motion of objects and the quantitative analysis of that motion. But this can be tricky business if you really think about the fact that everything is in constant motion. When we say that a car is moving at 100 kilometers per hour on the freeway, we are ignoring the fact that the surface of the Earth is rotating around the center at about 1700 kilometers per hour at the equator. Earth is also moving around the sun at around 30 kilometers per second. The entire solar system moves around the galactic center at 20 kilometers per second. And the Milky Way galaxy is moving through the universe at about 230 kilometers a second. So it's not completely wrong to say that the car is actually moving with this incredible speed as well.
So basically, all the little speeds that the car has in comparison to 230 kilometers every second, obviously, you'd be adding a third decimal place or something to that, right? Or even less.
Meaning that in a certain context, there's practically no difference between flying in a plane and sitting still in terms of absolute velocity.
Which doesn't really exist. Absolute velocity, like what are you relative to? So even the speed of light itself is not relative to anything. It's just always observed to be 300 million meters per second. You'll see that later in the grade 12 physics class. But yeah, so the idea of an absolute relative reference frame, I'm surprised he even said that there, because the rest of the stuff he's saying is pretty good. He must not have, or he might not be focusing on the higher level physics, or he just doesn't know about it. I'm not sure which, but yeah.
But that's why we tend to discuss relative motion. We don't notice the movement of the Earth and the Sun and the galaxy in our everyday lives. To us, the Earth seems to sit still, and a few dozen kilometers an hour may be insignificant in the grand scheme of the universe, but it's a big deal to the cop with a radar gun ready to pull you over.
SG.
So we often discuss motion that is relative to the surface of the Earth. When we do this, we are assigning something called an inertial reference frame.
So I don't think he talks about inertia. He might later on, actually. Inertial reference frame. He doesn't talk about it yet. I'll pause there for you. A reference frame, is what we talk about. Like, oh, I'm moving relative to the Earth or not. An inertial reference frame is a reference frame that isn't accelerating. Like there's no accelerations. And so your inertial reference frame could be like a car driving along a road with a cruise control set. And basically the end result is that, you know, you're pretty justified in thinking that you're not moving relative to that car. And you would feel like normal, like you'd just be sitting like normal. Where things change is if the car starts to speed up or turns and undergoes accelerations, then you'll feel forces on you in that car. And there's a lot to talk about there later on. So we're just not talking about that stuff yet by saying inertial reference frames that aren't changing their velocity themselves, because that invokes a lot of other conversations later on that we'll have fun with. Yeah, so.
This is the object or person or location that we pretend is completely still, and we assess the motion of other objects relative to this inertial reference frame. For example, if we treat the Earth as an inertial reference frame and we ignore its rotation and movement through space, it becomes meaningful to say that this car is moving directly north at 100 kilometers per hour relative to the ground. But if we are inside the car, moving with constant velocity, it seems as though we are not moving, but rather that the surroundings are rushing past us at 100 kilometers per hour.
And specifically, you're not moving relative to the dashboard and the chair around you and stuff like that, right? And so, you know, if you look and you see the things rushing past you, you could think of them as moving the other way. Clearly, you're well aware of what's really going on. But there's a weird practical joke that I've heard of happening where if a vehicle is being towed like this, when I can't remember if I actually did it to someone or not, but if you have someone napping in the passenger seat and there's a transport being towed like this, you can go up like behind the transport and then like wake up the person screaming, you know, saying like, "Oh my God," you know, pretending it's maybe a transport head-on collision. Kind of a cruel practical joke, but the person would basically see the speeds, how they interpret, I guess, that the transport would be coming towards them. But, you know, part of that reference frame analysis there, though, is just thinking of. All right. So back to the show here.
The car has become the inertial reference frame that is standing still, and everything is in motion around us. It may seem strange to pretend that the car isn't moving, but remember, it's just as incorrect to pretend that the Earth isn't moving.
And more importantly, you're not really pretending it's not moving, you're just saying it's not moving relative to you, you're not moving relative to it, which is all true in that scenario, of course, right? But like you said, it's basically the idea of all motions relative is a very important thing to realize.
So it really is all relative. Imagine you are sitting in a moving train. You toss a ball into the air and catch it.
I'm gonna leave that stuff for later. That's getting into other things we don't need to worry about yet. So you know, just a quick application of this. You have a red Corvette, doesn't matter the red, I suppose, moving at 60 kilometers per hour. But it's moving at 60 kilometers per hour, but there's a twist. The tires aren't twisting. They're not going around and around. What are some possible explanations? Obviously, you might think of something like it's on a trailer or whatever, right? And so, you know, the statement should have been like the Corvette's moving 60 kilometers per hour. I suppose it could have said relative to the ground, but then there'd be extra information, right? It would have zero velocity relative to the trailer, right? So it would have 0 kilometer per hour speed relative to the trailer. Hopefully, anyways, as long as someone tapped these straps and said, of course, you know it, that's not going anywhere, right? All right, so if you don't know that, you got to watch more YouTube videos. Soccer ball, this one's cool. So this is the soccer ball shot from a truck. I'll just do my version here, soccer ball videos. Ball shot from a truck. So a little clip of this experiment that they did. So they have a truck moving along at, say, a very specific speed, say it's 20 miles an hour or something, because they're American. And they have this air cannon set up to shoot a soccer ball backwards, the exact opposite direction, at the exact same speed as the truck. And this is what it resulted in. So here we go. So that's the regular speed. And then you go in the high speed, and it's just.
Check the high speed. It really looked good to the naked eye. But the judge in this case is the high speed.
Oh God, it's like a cartoon. It's just in the air.
So it literally just falls straight down because the ball isn't moving relative to the ground because the two velocities combined, right? So you had the velocity forward and the velocity backwards canceling out to zero. So the ball was moving relative to the truck. If you're in the truck watching it launch out the back, we saw in the video launching back, if the ball is moving relative to the truck, but it's not moving relative to the ground. Just kind of neat. And then this is the Bay Street in Sault Ste. Marie where I grew up. Police story. So I'm driving the big red van that I had in high school. It was an upholstery company delivery van that my dad bought for the family business. And then I ended up taking it over because he didn't need it as a delivery vehicle. Because the other delivery vehicle transmission was actually fine after all. Anyways, long story short, Bay Street, if you've ever been to Sault Ste. Marie, is a one-way street with like 5 lanes. I have no idea why. It's so weird. It's like it's way more lanes than you need in one direction. But so I'm at the stoplight, and so I'm at the stoplight, and I have music playing and whatever else, and I look, and I notice there's a police officer beside me. Okay, so I'm like, oh, police officer beside me. I better like turn my radio down and like behave myself here, whatever, right? And then, okay, worst thing happens. All of a sudden, for some reason, I start like rolling out into the intersection, going through a red light. Okay, so I'm stomping on the brakes to the point where I'm surprised I didn't burst a brake line. Like it was actually a good test of my brake system at that point in time. It's a little bit of an older van, right? So good to test things once in a while. Anyways, I'm stomping on the brakes. Finally, I realize what actually happened. Think about what would have happened there to make me think that I'm going into the intersection. So the police officer pulled up beside me. All of a sudden, that police officer was my reference frame. I'm noticing it. My position is fixed in my mind relative to that car. What happened to make me think I was going into the intersection? Well, the police officer must have got a call and started backing up. I wasn't expecting that, and so I got tricked into thinking that I was going forward, and yeah, so your brain can really trick you into thinking you're moving when you're not, and vice versa. Okay, so this little video here, relative velocity of trains, is kind of trippy here. Trains, relative velocity of trains. It's a weird little video that someone took, and so you can clearly see there's like a train going by, and so your assumption right now is probably, at this point at least, your assumption right now would be that you're stationary and the train's moving past you maybe. But if you catch glimpses of the corn behind you, you can tell like, oh wait, you're moving too. Then it keeps going, but basically this video messes with your brain, trying to fix a reference frame and figure out what's going on motion wise, where this is. Went on vacation somewhere, taking a little video, and then probably watched it afterwards and got all confused about what was really going on, right? And so finally that train goes by, and then you're like, oh wait, we're not moving anymore. And you can tell because there's 2 different reference frames here, right? Everybody's waving, bye, bye, right? So I guess the train they were in was moving and then came to a stop, and but man, it's so hard for your brain to like find those reference frames. That's something that your brain always does try to do. Okay, so just I try to throw in as many things as I can to get you thinking about relative reference frames, and why they're important, right? To figure out what's really moving or what that even means, right? So with reference points for things, directions become important. And so that's now time for us to talk about scalars versus vectors. Vectors have directions. They have a size and they have a direction, whereas scalars just have the size. Okay? So, or the magnitude. Magnitude is another name for size of something. So if you're looking for directions of things, labels, this long acronym can sometimes be used. It's not really one that people see, but north, south, east, west, left, right, up, down, forwards, backwards, positive, negative, whatever, right? So lots of different directions that might be quoted for things, up or down, and yeah, there you go. Whereas this is just the size or magnitude of the quantity. There's no direction listed. Okay, and lots of quantities that can have kind of both versions. So like distance, I went 3 meters, right? Versus like I went 3 meters east, right? Or sorry, I'm at a distance of 3 meters, from something or whatever. And then it's like, oh, well, I'm 3 meters east of something. Okay, what I had just said was the idea of I went 5 meters, so I traveled 5 meters, so change in distance. And then this would be a change in position, which is the fancy word is displacement. Okay, so I went 5 meters west. at a displacement of. So this one's just a location or a position, whereas this one's like you moved. Okay, so that's meaning. We're going to be seeing this as you're actually going to be seeing this soon as like D2 vector, take away D1 vector. In other words, where you end up, subtract where you started, gives you your displacement, okay? How far you've moved. Something like speed, I just have a speed of 4 meters per second, whereas if you'd say, oh, I'm going 4 meters per second in a specific direction, right? So then it becomes a vector. So sometimes there's different words, like speed is the scalar version, velocity is the vector version, and so on. And yeah, so there you go. Obviously, like a lot of people just tend to use these two words interchangeably, right? But really, there's a difference, a slight difference there. So the weird thing about vector displacement, and honestly, people make way too big of a deal of this sometimes, I think, but it only, so this down here is like, this is often overemphasized, and it's like, seems like it's the most important thing ever in a physics class or something to some people. But so since it's only the change in position that matters, right? Start compared to finishing. A strange consequence would be, what's the displacement of, say, an IndyCar race car? I have a friend who's actually at Talladega right now for enjoying all the races and that in Talladega, wherever the heck that is. I'm not a big race fan, but he's into it. He's a fellow Jeeper, but also into fast cars as well. Anyway, so yeah, 500 laps later, right? The cars have gone a long way, but they start at the start. They start at the same line they finish at. So the answer is they have zero displacement. Okay, so it's 0 meters, and so the distance traveled and this average speed are obviously a lot more, but the displacement and the velocity at the finish line averaged out for the race is absolutely just 0. But it's kind of meaningless, right? It doesn't matter, it doesn't mean anything. But so it gets talked about a lot. I have to tell you it, but I'm not going to harp on it. Okay, like maybe some textbooks or teachers or whatever might. All right, so choosing reference frames. This one's a little weird. So picture the blue person, green person, and red person. 6 people just drawn with colors. So this person, you can tell what they're doing. They're moving to the right, the quickest of everybody. This person's just stopped, no dots at all. And then this person's moving slow to the left. So the task is to think of like what the dot diagrams would look like from other people's point of view. So what would the dot diagrams look like of the motion of the other two from the blue person's point of view? Okay, so we're going to have the blue person fixed in place. So the blue person is going to be fixed in place, whatever, close enough. So that person's now the stationary person, their dot. Let's just put their dot on them there. And then what would, I might have to move this around. That's a hint, I guess. Let's put them in the center from now on. So what would the green person look like? Well, the green person, you'd see them, remember the car and the video and whatnot, see it going the other way, right? So if I were to put dots in that kind of spacing, that's what the green person would look like. So they'd be going like that, let's say. Okay. So green person's kind of going this way. I'll put them over here, so it's whatever, like that, right? So basically that same velocity as the blue person was. And then, let's see if I can move that up a little. What about the red person? So the red person, if you think about it, it's going to look like they're going even faster that way, right? So you're going to have this size of arrow and this size of arrow. So I'll put it like that. And so I'm going to use those where it's going to be the red person's going to be going even faster this way. So the red dots would be this far apart. And I'm just going to put a finger span across the smartboard here to try and have lengths that make sense, right? So that person's going even faster, so they're over here already or whatever. And nothing's drawn to scale here, but just relatively, no pun intended. We need to look decent. Relative, that word, right? Can't use it for as fast and loose when you're doing a lesson like this. So the dot diagrams from the red person's point of view. So red person point of view, they're stationary, they're just here. And what would everything look like from that person's point of view? So they're going to the left. And so you'd picture the green person moving the other way, right? So dot, 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 like this. The dot's going this way for the green person. Put them along here somewhere, whatever. Going this way, right? The opposite of what the red person was going. And then what about the blue person? So this is just something that you need to kind of be able to think through, right? So with the blue person, what would the, sorry, from the red person's point of view, what's the blue person doing? So red person was going that way, they're going the opposite way. So I guess they'd be adding up basically, right? So the distance this person goes combines with the distance you go the other way, and so they're going to be, double, right? That distance, that amount. So picture this kind of a arrow system going the other way now. Yeah, it's just the opposite of what we said for the red from the blue point of view or whatever, right? So I think that's right. So we'd have, the double distance there. So I'll just do that and put it this way. Oh, they didn't stay grouped, but you get the idea, right? I've got double like that. It was supposed to be down here for that one. That. So there we go. I feel like maybe I made a mistake there, but I don't want to harp on it for too long. So correct me if needed. So it's often done where you sort of establish your reference frame, and I was tempted to do that here on this page. Let me just go up to my picture of Earth. First of all, here, copy and paste on here. So picture, actually, no, there's the Earth is there in the picture. So basically, you could picture the car's speed relative to various reference frames, right? So the trailer itself could be a reference frame where you're listing like your X and Y reference frame. You're up and down, left and right, east and west, or whatever. Or we could be looking at the Earth as your reference frame. So in this case, I'm just putting an X and a Y coordinate on, so we can look at the dimensions there for that. So picture like in a boat. You're looking at your velocity relative to the boat. The green one could be described. So you're probably 0 unless you're walking around, and then or it could be relative to the shore. In which case, you're going to have the same velocity as the boat, maybe if you're stationary in the boat, and so on. Right. So just visually seeing where you're choosing a reference frame can be labeled like that. It's not something we're going to do a whole lot, but it just makes sense to show. I wish this program still worked, but it was exactly this kind of thing. So I do this instead now, but this one was, and I started doing that afterwards when I saw this as well. But this used to be like the river used to flow and the boats were going the other way, and this person was walking, and so you could hover over the blue person, let's say, and you'd see like what way the trees look like they're going relative to you, or the lampposts or whatever these are, and which way the boats. So whatever you hovered over, it would pin that thing as the fixed reference frame, and you'd see everything else's motion relative to it. But none of them work anymore. I tried and tried and tried to get links going, and so it's like it's close, right? This is a question or a student worksheet to do with that applet. It just doesn't work. I've tried and tried. If anybody can find this thing working, that'd be cool if you could send that to me. So with directions, forwards versus back, and up versus down, north versus south, you're pretty much going to invoke positives and negatives. Maybe not yet, but basically pretty soon it's going to be part of our daily routine, is thinking of positives and negatives as just opposite directions. Okay. So that's it for this lesson, relative motion and scalars and vectors and so on. I added in a question here as well. So this is I live in Westport. This isn't my house or anything, but this is just like when you search Westport, where it is, you say I'm going from Westport to somewhere. So I just picked this weird spot that happened to be labeled Blair's Settlement, wherever. I'll have to go check it out sometime. But this path, right? The questions to do with it are like, what's the total path distance, and what's the displacement, and so on. And so you should be able to figure that out, where if you're adding all these up, it's your distance traveled, right? So total distance traveled, you can see you've got the numbers there. And then you can also in Google measure like the direct path. And so there's a word associated from the lesson to do with that. But along the way, of course, here, dot diagrams for showing motion, and I think you'll find it's all pretty similar. The only other part here, I want to make sure you recognize that this scale diagram of your route to school, I'm intending for it to be something along the lines of this. You could do it in Google if you want, actually. Usually in the past, I just had people sort of dry with the idea of like, oh, I go on Highway 10 and then I turn and then I go to the school or whatever, right? So it doesn't have to be super detailed. I'm not looking for that information specifically. I'm actually just getting the same ideas as this, right? Of this question here in particular, right? Is your distance traveled while going to school the same as your displacement, your house to your school, from your house to your school? Explain, what would have to be true about your path to school for this to be the case. I'll be looking for that answer for sure in the homework checks. All right, checks, whatever you call them, submissions. Yeah, so that is it for me, and bye for now.